Thank you. I'm excited too, if that's a good thing. So yeah, today I wanted to talk to you about creating a quantum algorithm. I decided, instead of just talking quantum theory, I also wanted to show you what quantum programming actually looks like, and that's why I'm going to do a live demo. So I'm very happy that at least some of you decided to show up and to do some different kind of session. So my name is Johnny. I am from Belgium. From Belgium all the way here to Finland. I'm not going to talk about myself a lot. The only thing that I'm going to tell you is that if you see this QR code, if you follow the link, and you follow the links in the bottom of each slide, it already takes you to a GitHub repository that contains everything that I will show you today. So all the code examples are there, even code examples that I did not show you, and the whole slide deck is actually already there. So you could basically just walk out right now and just look at it online. But if you decide to stay, I can tell the story with it, of course. All right? So first, I'm going to do a little introduction, like a 15, 20-minute introduction on what quantum computing is, and then I will spend the rest of my session doing live coding and hopefully make you understand what a quantum algorithm can actually look like. So before I talk about quantum computing, I want to take you back to my childhood. Why? Because when I was a teenager and I was attending school, a teacher actually knew that I was playing around with writing little computer programs. My mom had a very old MS-DOS computer, and I wanted to learn some programming because I was basically creative as a child, but very lazy. So creative as a lazy person is writing code. So the teacher came up to me and told me, yeah, I have a little challenge for you. So you know a chessboard. A chessboard has 64 squares. You have different kinds of chess pieces. And one of the chess pieces is represented by a horse. That's the knight. And a horse or a knight can do very specific jumps. It can jump, for example, on the left-hand side from that specific position to 8 different positions on the board from that origin. The teacher told me, could you write an application that actually tries to find a unique path that visits all of these squares just once? And on the right-hand side, with my beautiful paint skills, I actually did one of the possible outcomes. And back in those days, when I was, I don't know, 14 years old or something, I said, okay, this is actually very simple to solve, because you basically just brute force, you just try, walk around, and when you're stuck, when you can't jump anymore because you visited all the squares, you just take a step back and try a different route. Now, when I was 14 years old, I never heard of recursion. So I basically put 64 for loops nested within each other to make that work, or at least I thought that would work. I pressed start on this old MS-DOS computer and nothing happened, no output. So it was processing. It took a while. I waited for minutes, I waited for hours, I even waited overnight, and still I didn't get any output. And this was the first time in my life that I got acquainted with something that is called an exponentially large problem. It can actually be that you take the wrong route every time, and you spend ages trying to find the correct route, because there's so many permutations, there's so many possible routes that will fail, and there's only some of them that will actually succeed. So for this old classical computer, it was not possible to solve this problem in a matter of minutes. So this was the first time. Of course, today in computing we have the same problem. We have problems today that we cannot solve with classical computers, so we are looking to different kinds of computers to hopefully solve these kinds of problems. Quantum computers are hopefully computers that can help us with that. And what is a quantum computer? Well, a quantum computer is a computer based on the quantum principles, or the principles from the quantum mechanics space. Two principles that we are actually going to leverage within quantum computing is called superposition and entanglement. You probably heard about those. Superposition basically means that on a very small scale, so on a quantum scale, so very tiny particles, they can have a property. For example, the spin of an electron in the left-hand side image. The spin of an electron is kind of a binary property. It can be up or it can be down. So for us, it's very easy to understand. It's binary. Up can be, for example, 0, down can be 1. Now, superposition means that in practice, the property can also be both at the same time. That's not really true. It's not both at the same time. It's just basically not existing yet. So it's kind of a probability thing. So it can be up or it can be down, but let's say the universe hasn't made that decision yet. It's only when we make an observation that it will actually flip to either up or down. And this is what we call superposition. It only works on a very tiny scale. So it only works for electrons, atoms, stuff like that. They have these properties. Some of these properties can have binary states, and they can also be in a state of superposition. On our macroscopical level, this does not work. So we never see this happen because it just doesn't happen at our scale. The only thing that I sometimes have is like when you have like this old school USB-A connector, you try to put it in the USB slot, it never fits. You can turn it around multiple times. It's only when you observe the slot that it basically collapses to its correct orientation, and then it will fit. That's the same thing, but this really happens on a very tiny scale. On the right-hand side, there's an image that represents entanglement. Entanglement, it's even more weird. When you have two microscopical objects or quantum objects that have a quantum superposition, they can be in a form of entanglement, which means that they influence each other. If you observe one of the two, it will collapse its superposition and it will be either one of those binary values. And the other item will immediately collapse to the opposite position. And we don't know how that works. There's no scientist that actually can prove how that works. It even works on large distances. So when you have entangled quantum objects and they are very far apart, if you observe one, the other one will collapse to the opposite state immediately. There's no delay, so there's no communication. We have no idea how that works. But it does work, and we can leverage these things to actually build computers that can do very, very weird things. By the way, these are my drawing skills. This is not what it looks like in real life. This is just a representation that I did to better explain what superposition and entanglement is. Welcome to the new people. So, yeah, why are we building quantum computers? I already told you, because we have very hard problems that we still cannot solve today. Problems that can actually, when we can solve them, can actually help us to save the polar bears. Because climate is really a thing. We really need to look out for our planet. We need to spend less resources on the things that we do. So if we want to solve a very big problem, we are basically throwing millions of classical computing instances towards that problem, and hopefully we can solve a part of it. But of course, that takes energy. The same with AI and machine learning. We spend a lot of energy today just to generate stupid pictures like this. I'm sorry, polar bears. But there's all kinds of things, like drug development, for example. When we create medicine, when we design medicine today, we have kind of an idea how the human body works, but not in detail. We don't know every detail. So we basically try something, we build some kind of medication, and we test that medication on animals. If the animal dies, we go back and try again. It's the same as we developers. We run our application, it fails, we try again. But of course, with medicine, we can't try on people, because when a person dies, that's horrible. But for some reason, animals dying is not horrible. Again, with quantum computers, we hope to have that exponential, we hope we can solve those exponentially large problems or solve them better, so we can basically create some kind of a simulation of a human body. And when we have that simulation, we can run that simulation a couple of times and test our medicine that way. And it's the same with AI and machine learning. I already told you that we spend a lot of energy on AI and machine learning today to make these models that are almost perfect, but actually it's a statistical thing. In order to make a perfect model, you basically need to train it for an indefinite amount of time, which we don't have. If we have faster and stronger computers, we can make those models better. So again, quantum computers, when they are better at exponentially large problems, they can actually solve this problem for us. I'm not going to talk about the other things because I don't have time. I want to show you other cool stuff. But let's go back to basics. We all know classical computers because we are IT people, right? We know that in a classical computer we have things called bits. They can have two distinct states, 0 and 1, and we can combine those zeros and ones and represent all kinds of data. We just throw them together, we decide on a protocol, or we decide on a format, a data format, and we know what the data represents. Now, in the quantum space, we're going to do the exact same thing. I told you we're going to leverage quantum objects that can be in superposition, but when they are not in superposition, they also have binary properties, like the spin up and spin down from an electron. And this can be represented by 0 and 1. So it's the same. We will think in the same way. The only difference is there's a kind of a different notation. If you see something like this, you know it's a quantum 0 state and a quantum 1 state. This is called the Dirac notation, which is basically a vector notation from linear algebra. So now you know it's a quantum vector that represents the state 0 and the state 1. We can also combine in the quantum world, so we can combine states for qubits or quantum bits to represent data. Again, the same thing. So we don't need to learn new things here. Everything from the classical world also works in the quantum world. But things become interesting when we involve superposition. So when we involve superposition, we basically create a probability expression that will express how much probability there is to collapse to 0 and how much probability there is to collapse to 1. And these are the alpha and beta values. And now it gets a little bit mathematical. When we do classical computing, it's basically also mathematics. It's logic, it's pure logic. When you have zeros and ones, you can do operations on them. You can do AND and NOT and exclusive OR and other kinds of operations. And those operations are quite easy to do from the back of your head or from the top of your head. You don't need a piece of paper for that. But in the quantum world, when you were working with superposition, things get complicated, and we need some additional mathematics, linear algebra, to actually calculate what the result for a specific operation is going to be, and that's why I'm showing you a little bit of this math. Now, this expression always ends up being 1. 1 meaning 100% chance. It's 100% chance of either being 0 or 1, and it's just divided between those two, alpha and beta. If you look at this expression, it means that your alpha value, the absolute value of your alpha value needs to be squared, and you need to add the absolute value of beta, and that needs to be squared, and the result needs to equal 1. Now you're looking at me, why are you taking the absolute value when you're doing a square operation? Because mathematicians are assholes. Alpha and beta are complex numbers. So we are working in three-dimensional space. When we look at the superposition state vector, alpha and beta combined, two complex numbers, 3 dimensions. You probably know, again, mathematicians, I hope there's no mathematicians in the room, but when they can't solve a problem, they invent new dimensions, and then they can solve their problems. So the state, the superposition state, is actually a state that can be represented in 3-dimensional space. And if you look at the perfect 50-50 superposition, that's going to be something like this. 1 over square root of 2 is half, and 1 over square root of 2 is half. Why? Because you need to square it. So 1 over square root of 2 squared is half. Half times 0, half times 1 is 50-50% superposition. And this is what happens in a quantum computer. If you put your qubit in superposition, it can be this value. And then you can actually very carefully change the superposition state to some different vector that has different probabilities. It can be 75-25, as long as the total is always 100%. Now, because math is hard, we humans like visual representations of that. It's actually nothing more than, as I said, a vector in 3-dimensional space. So we have a sphere. This is our vector space that we define specifically for the state of a quantum bit. So if you remember your linear algebra, which I actually failed in university, because now I know what it's useful for, not back then. So this is our vector space. It has 3 axes, x, y, z, so 3-dimensional sphere. The length or the radius is actually 1, that's our 100%. And we can put a vector that originates from the central point, and it can actually point wherever on the surface of the sphere. On the right-hand side, you will see that vector psi or phi or whatever, pointing somewhere up. Now, if you look at the distinct 0 and 1 states, those live on the z-axis. So the 0 state is pointing way up. So that's 0. And when the vector points down, this is 1. Everything in between, which is an indefinite amount of possibilities, is some kind of superposition. Now, if you have a perfect 50-50 superposition, your vector will live somewhere on this plane. combining the x and the y axis. Why? Because this plane, when the vector points right, for example, is exactly in between 0 and 1. So the distance it needs to travel is the same. Now, if you look at the right-hand side image, so that vector points somewhere upwards. Doesn't really matter where it points exactly. What are the chances it collapsing to 0 or 1? Anyone knows? Are the probabilities higher of it collapsing to 0 or higher of it collapsing to 1? Higher to 0. Why? Because it's closer to 0. So this is why I like to show you that graphical representation, because now you can see indeed that the chances are higher. And we already talked about linear algebra. You can also use some trigonometry to actually calculate the percentage, because you know your sines and cosines. Basically, when you do a little dotted line here and a little dotted line here, you know the angle of your vector. You can actually calculate what the percentage of chance is to collapsing to 0 and what the percentage is collapsing to 1. So this is just basic trigonometry. And if you dumb it down a little bit to 2 dimensions, that's exactly what we're doing. If the vector is exactly in between, which is, as I told you, 1 over square root of 2 plus 1 over square root of 2. The angle is pi over 2. You can actually use the sine and the cosine, and the result you will get is actually half-half. If you do it on the right-hand side, where your angle is 2 pi over 3 radians, and you do your sine and your cosine, you will get 1 over 2 and square root of 3 over 2, which is actually 1/4 and 3/4. Which is 25-75%. So this is what you need to know about calculating your probabilities when a quantum bit is in superposition. So it's a little bit more mathematical because, of course, you can't do it from the top of your head. All right, now that we know this, why is a quantum computer more powerful than a classical computer? Well, if we start combining these superpositioned qubits, we actually go exponentially. So if you have a 2-qubit system, you have 4 probable values or 4 probable outcomes. You have 0, 0, 0, 1, 1, 0, 1, 1. Now, if you add a single qubit, it always doubles. So now you have 8 probabilities. For a 4-qubit system, you have 16 probabilities. And depending on the algorithm that you're writing, if you put all of your qubits in superposition, they basically represent all of your different outcomes at the same time. Now, if you really go very quickly and you think about it, if you look at a classical CPU, in order to double the power of your classical CPU, you need to double the amount of transistors that can represent bits. So that's quite hard to do. But for a quantum computer, if you want to double the power of your quantum computer, you only need to add 1 single qubit, which is quite powerful. Now, I don't work for the media. When I say in a quantum computer, when you add 1 single qubit, it doubles the power of the quantum computer. What the media does not tell you is that when you add 1 qubit to a quantum computer, you exponentially make it more difficult and more unstable to actually work with. So this is why quantum computers are not really a thing today. They exist, we can use them, but they're quite small. Not physically small, I mean they don't have a lot of qubits. Because when we add qubits to that system, it becomes exponentially more unstable because it's very hard to keep all of those qubits in superposition when we need to. So yeah, we're still working on that to actually make those stable by trying to find the correct quantum objects to put in superposition and all of those things. Now, if we look at creating an algorithm, we're actually in the level of circuits. You probably also know that when you're using classical computers, basically there's a bunch of circuits within your CPU. You can have specific functions that you can call on your CPU, and there will be a circuit connected to that, and that circuit will actually work with those binary numbers. In a quantum computing space, it's the same thing. We have lines horizontally representing the time and one of the qubits, and then we have different gates where we put those qubits through. Exactly the same as in the classical space. In the classical space, you have bits, you put them through gates, stuff happens at the other side, at the other end of the circuit, and in quantum, it's the same thing. This is actually the quantum teleportation circuit, because in the quantum space, you cannot copy values. You cannot copy the state from one qubit to another qubit. That just doesn't work in quantum. So if you have a very specific superposition state, you can never copy that to another item. You always need to perform the same steps in order to get to the same state. Except for this little circuit. This little circuit will actually teleport this specific state, which can be whatever, to this specific qubit. Very weird. Teleportation means that the original one will be destroyed. So you don't take a copy, you teleport it to another qubit, and the original qubit is destroyed, or at least the state is destroyed, not the qubit. That would be a very expensive quantum computer. Now, how this works, this is a little story about Alice and Bob. We know those people. Alice and Bob want to share some data. Alice actually has hold of the message, but Bob does not. So Alice wants to give the message to Bob. So the first thing that Alice and Bob will do, they come together. They will make sure that they have two qubits, and they will entangle those qubits. So this is qubit for Alice, this is the qubit for Bob. They basically, Alice puts her qubit in superposition. The H or Hadamard gate puts a qubit into superposition. And then they will do a C-NOT operation to actually entangle those two qubits together. And now they are entangled. A C-NOT gate is a very easy gate. It basically means when this qubit is 1, this one is flipped around the x-axis, which is just a NOT operation, because the x-axis, if you remember from the sphere, if your vector points straight up the z-axis, it's 0. When you flip around the x-axis 180 degrees, your state becomes 1, and vice versa. So it's a NOT operation. But it only works when this one is 1. When this one is 0, nothing happens. But this one is not 1, it's not 0, it's in superposition, which now makes these two qubits entangled. Now, they started out as the 0 state. Now they are entangled and in superposition, of course. And the message qubit is some arbitrary superposition state. We don't know. Now we entangle the message qubit with Alice's qubit. And this is where things become interesting. Now Alice and Bob, they can go far away from each other. Bob can take the airplane to Australia if he wants. Alice can stay here. And the following thing needs to happen. Alice measures her qubit. And when she measures or observes the state, she collapses the qubit into either 1 or 0, the two base states. Now, when the result is 1, she will call to Bob, or she will send an email or a WhatsApp to Bob telling him, I got 1, which means you need to put your qubit through the X gate. Again, the X gate, 180 degrees around the X-axis. Then she does the same thing with the message qubit. She measures it, destroying the original state, so the original message is destroyed. If she has 1 as a result, she again calls to Bob, and she tells Bob to flip his qubit vector around the z-axis, 180 degrees. And for some magical reason, the exact same message state is now teleported to Bob's state. And this is a circuit you can actually run. You can run that on Azure Quantum, on a real physical quantum computer if you have time, because there's a long queue, because everyone is trying all of these things. It works. It will actually work, which is quite spectacular. Now, very quickly, Azure Quantum is one of the resources that Microsoft has in Azure, and Microsoft is working on building their own quantum computer. But they're not finished yet. They are working on a very hard way of doing a quantum computer because they think that is the best way of building stable quantum computers. So they are working on a topological, on a quantum computer that is using topological qubits. I tried to read the paper for that, but I have no idea what it's about. I'm not an engineer, I'm not a physicist, so I just don't understand what they are doing. I hope they understand what they are doing, because they're not ready yet. There's other vendors, other hardware vendors that do similar things, but they use different kinds of quantum objects. For example, you have IonQ and Quantinuum. Those are two companies that are building physical quantum computers using ion traps. So ion traps are basically ions that they use to represent a qubit, and they use lasers to actually change the superposition very carefully. So by using lasers, they can actually change that vector in that sphere to have a different kind of superposition state. Then there's QCI and Rigetti, and by the way, also IBM. But IBM is not available through Azure Quantum. They are using superconducting qubits, which are electrons, and they can change the superposition state by using microwaves. So each company is basically trying to build their own quantum computer in their very specific way because they think that is the best way to do it. And then this is a new one, Pascal, using the neutral atom. I haven't looked into that, so I have no idea how that works. Now, Azure Quantum is basically a workspace where you get access to one of these quantum computers. The one from Microsoft you can already target, but they will basically do a simulation, and they will tell you how many resources you will need when they eventually have the quantum computer finished. These ones have simulators available, but they also have the physical quantum computers available. But if you want to run your algorithm on one of these, there's a long waiting line, so you need to wait for hours before your stuff actually gets run. And how it works is pretty much the same way as .NET works. It works by first taking Q#, which is the language from Microsoft for writing quantum algorithms. They will compile that down into an intermediate language, just like .NET. And .NET and C#, they go to intermediate language. In the quantum world, we go to quantum intermediate representation. And then the quantum intermediate representation is then compiled down to machine code by the very specific hardware vendor. So each hardware vendor basically creates a driver for their hardware. They will compile QIR down to machine code for their specific machines. Now, Q# is a language that we can use today to learn about quantum. Maybe you're super smart and you have the new quantum algorithm already available. But I'm going to show you a very simple quantum algorithm because we have 25 minutes remaining. So let's see where we can get with this. So I've created a game. I did not create this. This is actually a game that's been invented multiple decades ago to prove a very specific aspect of quantum computing. And I'm going to use this just as an example, because this will take me around 20 minutes to explain to you, and hopefully you will understand, and you will understand what the power of quantum can be, and also how you need to think out of the box to actually do something useful with a quantum computer. It's not easy, so please try to stay awake and try to follow what I'm going to talk about now. So the game is called a CHSH game. Those are just the initials of the people who invented this specific algorithm. And it's a game of luck. It's a game of luck. So we have two people, or animals in this case, playing this game. We have Jaakarhu and we have Pingviini. This is my best Finnish accent. And they are going to play the game. And why is it those two animals? Because they can't speak to each other. So the Jaakarhu is living on the North Pole and the Pingviini is living on the South Pole. So they can't talk to each other. And both of them will get a random number, 0 or 1, as input. Now, when both received their random bits X and Y, they need to output random bits A and B. Now, when they do this, the expression in the bottom needs to be true in order to win the game. So when the input X and Y multiply together equals the exclusive OR for A and B, then they win the game. But they can't speak to each other, so they can't influence their decision, and they don't know what the input X and Y for each other is. Very weird game, right? Now, if you think about this, and if you put this in truth tables, you know when X is 0, 0, 1, 1, and Y is 0, 1, 0, 1, you know the result of the left-hand side of the expression, 0, 0, 0, and 1. And for the right-hand side of the expression, you can do the same thing. If you have A and B in all of their different values, and you do the exclusive OR for A and B, you get those values. So look at this. How can they win this game? Well, basically, when they cheat a little bit, and maybe they're together in a zoo somewhere. They're together in a zoo, and they know that they're going to need to play this game in the future. They can basically tell each other, you know, when we ever need to play this CHSH game, we're just going to output 0. Is that okay? Okay, so we're just going to output 0. Then the zoo sets them free. One goes to the North Pole, one goes to the South Pole. For some reason, they now get a telephone. They need to play this game. Okay, remember, we needed to output 0. So if they both output 0, you look at the right-hand side, the only thing that happens now is the top line, so 0, 0 becomes 0. So the output of the right-hand side of the expression is 0. Now, in how many cases is the left-hand side of the expression 0? In 75% of the cases, 3 out of 4. So basically, when they talk to each other beforehand, like I told you, and they they decide to always output 0, they have a 75% chance of winning this game. If you do this at a casino, that's a very nice winning percentage. So in the classical world, they can win this game in 75% of the cases when they always output 0. I'm going to show you that in the quantum world, they can increase their chances. But let's start with the classical one. So we go to something that is called Q#, which is the language to write quantum algorithms. And we're going to implement this classical version of the game. Then I'm going to implement the quantum version, and we're going to compare. So we're playing this game. All right, let's create a variable called number of games equals 10,000, because it's a statistical thing. We need to run it multiple times in order to know what our win percentage is. And we need to keep a mutable variable with our classical wins, and they're going to be 0 to start with. We're going to have our quantum wins, and they're going to be 0 to start with. And now we're going to run the game 10,000 times. Yeah, GitHub Copilot, I don't need you now. So for I in 1 to number of games. Now it doesn't look like I'm smart. Now I'm just typing what it's proposing. Whatever. So, okay, we play the game. The first thing is we need to get those random input values, x and y. Those are random, so we need to generate them randomly. So let a tuple of x and y equals calling a function generate random bits. So in Q#, you also have the concept of running a function, an operation. So I can create a new operation, generate random bits. It takes no parameters, and it returns a tuple of 2 booleans, true or false. I told you, we need to work on this classical version first, but I'm going to use a little bit quantum in this classical version. Because if we can never make quantum computers stable, the only thing that they can already do today really good is generating real random numbers. Like a classical computer only does pseudo-random numbers. Like when you have a quantum computer that only has 1 qubit, put it in superposition, measure it, true randomness, nature random. Very cool. So I can actually use the use function to create a tuple of 2 qubits, Q1 and Q2. And I'm going to use the qubit factory function to not generate a qubit, but to allocate a qubit to that specific variable. So because qubits are very expensive, you know this from C#, for example. In C# it's called using. In Q# it's called use. You basically use something that is very expensive, and when you're done with it, you deallocate it automatically when it goes out of scope. And then the system has the quantum bit available again for the next purpose. Now we put those 2 qubits in superposition by putting them through the to the H gates. So now they're both in superposition. And now I can return a tuple where we do a measurement for the first qubit, and we do a measurement for the second qubit. Now this looks a little bit weird. What I'm basically doing, because Q# is a little bit like C#, it's a very type-safe language. So the result of a measurement is always 1 or 0. And 1 or 0 are of type result and not of type Boolean. So I need to compare this measurement result to 1. And if they're the same, it's true. So that's how I convert 1 to true. mResetZ is actually a helper function that does a measurement. That's what the M stands for. And reset stands for the fact that after I've measured my qubit, I'm resetting it back to its original 0 state before I return it to the system. This is something specifically to Q#. When you have a qubit that is in the state 1 or is still in superposition and you return it, it goes out of scope, you get a runtime exception because you always need to put your qubits back into their original 0 state. The Z stands for measuring on the Z-axis. I told you the Z-axis, 0 in the top, 1 in the bottom, that's measuring on that specific axis. So now I have my 2 random numbers in a quantum way. Now I'm going to generate my A and B by playing my classical game. And of course, I need to provide my X and Y values. So this is playing the game in a classical way, and I told you they just need to return 0, 0 in order to have a 75% win chance. So operation play classical. I'm going to input 2 booleans, and I'm going to output a tuple of 2 booleans. And as I told you, we're just going to ignore the input, and we're going to return false and false, or 0 and 0. That's it. The only thing I need to do now is compare the two sides of the expression. So I'm going to create a variable left-hand side of the expression, and the left-hand side was just a multiplication of 2 booleans. I can't multiply booleans together, so I need to convert them to integers. So I have a helper function that I can use, bool array, not bool, bool array to int, and I'm going to create an array containing only 1 bit x, and I'm going to multiply it with y. So basically, when you have a couple of bits, you can convert them to an integer. But we only have 1 bit, so 0 becomes 0, 1 becomes 1. Very easy. Again, it's a type-safe language, so you need these kinds of things. And it looks like C# because we need an extra namespace for this. We need to open or import the convert namespace to be able to convert from one type to the other. And now these functions should be available to me. Why are you not available? Bool array, okay, as int. Yeah, you need to know your base class libraries. Now we're going to do the same for the right-hand side of the expression. So let right-hand side be the exclusive OR. There is no such thing in Q# as doing an exclusive OR, unfortunately, so I need to do it a different way. So I can do the modulus I, or modulo, I actually don't know, for the bool array as int for A, plus the bool array as int for B, and divide them by 2, and the remainder after division will actually be your exclusive OR. That's the same thing. Again, in order to use the modulus I function, you need to include the math namespace. Modulus I seems to be correct. Now I need to compare the left-hand side and the right-hand side of the expression, and if they're equal, we know we won the game. If they're not equal, we lost the game. So I can do set in order to change the variable called classical wins. And I'm going to increase it if the left-hand side of the expression is equal to the right-hand side of the expression. And if that's the case, I'm going to add 1. Otherwise, I'm going to add 0. So this is not the most performant way of doing this, but now this is an if in just one line of code, which I like. So I'm adding 1 if it's equal, or I'm adding 0, nothing, if it's not equal. And that's it. Doing this 10,000 times, I can show the result in a message. A message is a console write line, basically. If you run this on a physical quantum computer, you get the result back in a JSON file. And that's your output, basically. It doesn't output on the physical quantum computer. It outputs in the result that you get back. So the classical wins is, I'm not going to do it this way. It's the classical wins divided by the number of games times 100. Jesus, 100%. So number of games is actually, it's an integer. Classical wins is a double, so I need to do int as double. This is very annoying. And then I'm going to round it to whole numbers so that it looks nice like that. So this is the classical way of running this algorithm. So run, and the result in the bottom is now 75%. So it's correct. Because we just saw 3 out of 4 times the result is going to be 0. So 75% is actually our win chance. Now let's make things a little bit more interesting. Those 2 characters or animals, they can actually use or leverage quantum effects to increase their win chance. So we're going to provide them with an entangled qubit pair. So we have 2 qubits. Those are going to be entangled, and we will provide one to Jakarhu and one to Pingvini. Now, they can go to their North Pole and South Pole. They can keep their entangled qubit, and they can now do very interesting things because they can influence each other. They still are not able to communicate to each other, but they can influence each other. And this is basically where quantum computing becomes very interesting. You really need to think out of the box in order to make something like this happen. And I told you, this is the two-dimensional version of all of the different states that we can have. There's basically different ways of measuring a qubit. When you measure a qubit, it collapses to a very specific state, 0 or 1. But you can actually influence that, and you can measure in different, what they call bases. So we have something called computational base, where the result is going to be 1 and 0. But we also have something that is called a sign base, where the result can be plus or minus. And this is actually positive superposition and negative superposition. I told you, you can measure on whatever base you want. So if you look at the block sphere, this one, you can actually influence where the vector collapses to. By default, it's the computational basis like this. But you can do the sign basis, then it will collapse to either here, or you can choose whatever base you want for your vector to collapse to. And this is what we are going to leverage for this specific game. So on the left-hand side, Karhu is going to measure in the computational or the sign basis. And Pingvini is going to measure in the negative pi over 8 basis or positive pi over 8 basis. And when they do this, you have basically 4 different outcomes. When the input values are 0 and 0, when the input values are 0 and 1, when the input values are 1 and 0, and when the input values are 1 and 1. So 4 different scenarios. So let's already put that into code. So I'm going to copy playing the games 10,000 times. I'm going to play not classical version, but the quantum version. There's going to be here a number of quantum wins. Quantum wins. This is quantum wins. When you copy paste things, you're going to mess up somewhere. So we'll see what happens. That's it. And I'm going to copy this function, play classical, into play quantum. Now, I can already prepare this a little bit. I told you we basically need to have 2 qubits entangled, so let's do that. So first we have a mutable tuple with the A and B output values. We'll assign false and false to them, and we will return them at the end of this operation. And now we're going to define the 2 qubits, so use tuple qubit Q for the first one and the second one. So those are the 2 animals, J and P. We have 2 qubits. We put the first one in superposition, and we use the C0 operation to entangle them. There we go. And then I told you, you basically have 4 different possibilities for your input values. So if x equals 1, you need to do something else. No. So so the question was, do you also need to put the other qubit in superposition in order to reach entanglement? No. You just put one of them in superposition, and then you use the C0 operation on the other one. So you use the superposition one as the control parameter, and you use the target one is the one that is not in superposition. And that is your entanglement. So if x is 1 or x is 0, and then if y is 1, else, whoops, there we go. So these are our 4 different options. So let's look at those options. 6 minutes remaining. There's going to be a lot of headaches, unfortunately. Sorry. So let's look at the first specific one, when both are 0. So what's going to happen? Karhu is going to basically decide when x equals 0, it's going to measure in the computational basis, and we have 2 possible outcomes. The outcome can be 0 or it can be 1, because now we collapsed the superposition of the left-hand qubit. Now, we can write that down. She outputs 0 or 1, and we also know that when this actually collapses to 0 and this collapses to 1, it influences the one for Pingvini. And you can see in red where I actually put the vector. So pointing to the right, the same as on the left. Pointing to the top, the same as on the left. But Pingvini is going to measure on the -π/8 basis. And now you can see that in order for this vector that already collapsed there, so it influenced this one, which also collapsed to the same position. By the way, I told you in quantum physics, it collapses to the opposite state. In quantum computing, it collapses to the same state. You can do a different kind of entanglement where it also collapses to the opposite state, but by default, it's the same state. And now you can see that if we measure on this basis, that this vector will probably collapse to this state because this one is closer. It needs just to collapse here instead of collapsing all the way over there. So when this is 0, Pingvini will also be 0. And when this is 1, Pingvini will also be 1 because they are closest together. And if you look at this in the 4 different versions, you will see that we can create an advantage. So let's look at the second one. It's the same thing. X is still 0. So we still measure in the computational basis, but now y is 1, and we're going to measure in positive π/8. And you see the same thing. If red is 0, blue is also 0. If red is 1, blue is also 1. And if we look at the final one, so we're going to skip the third one because it's the same story. But if we look at the final one, now because x is 1, we don't measure in the computational basis, we measure in the sign basis. It can be positive superposition or negative superposition. And if y equals 1, we measure in the positive π/8 radians. Now it's different, because when it's plus or 0, it's going to collapse to 1 here. And when it's minus or 1, it's going to collapse to 0. And if I put this in code, 3 minutes remaining. So let's think about this. So x was computational or sign basis. So that's easy. So I can do set A. So A is the output for the polar bear, equals m reset z for its qubit. And it's going to be the same. Now, I can't remember this by heart, so I always need to check. So one is going to be in the computational basis, one is going to be in the sign basis. So if I remember correctly, the computational basis where x equals 0. Yes, so this is the computational basis for x equals 0. So that's an m reset z. So when x is 0, that's measuring on the z-axis. When x equals 1, we need the sign basis. That's going to be the x-axis. All right, so these are those measurements. In Q#, unfortunately, you cannot measure on whatever basis. You can only measure on the x, y, and z basis. But in Q#, you can rotate your vector in every direction you want. So I can first do that. So I can actually do ry, which is a rotation around the y-axis, with π/4. I told you it's π/8, but it pisses me off a little bit, but it's a nice story because, dear developers, read your documentation. If you look at the documentation for the ry operation, you will see that they will divide your angle by 2. So if you do π/4, they divide it by 2, it's going to be π/8. So if you need π/8, you need to type π/4. Crazy. QP, so we rotate π/4, and again, I need to check, I need to verify which one is minus and which one is, I think the 0 one is minus. When y is 0, it's minus π. When y is positive, it's positive. And then after this, I can actually do the same thing. I can also measure in the z basis because we already did the rotation. So set B equals QP, and it's the same for the other one. Whoops. I can also put that behind the if statement, but whatever. That's it. Those are the 4 different options. Is anyone super smart, or did anyone look at the slides? What is the percentage of win? 85. It should be 85. So it's more, and it should be 85. So let's run. It's 86. It's even better. So classical wins 75%, quantum wins, now we win in 86% of the time. And again, this is pure mathematics. So if you, again, look at the mathematics in the bottom, you just know what your angle is. Your angle is pi over 8, depending on how it's oriented. It can also be 5 pi over 8, because minus pi over 8 is the same as 5 pi over 8. And if you do your cosine and your sine, you get your probabilities. You square those values, and now you know that it's 85% chance and 15% chance for those two specific values. Now, this is a useless thing that I just showed you. This algorithm does not make sense. I mean, you can't use this in your day job. I can't use this in my day job. I just wanted to show you how you need to basically think out of the box in a different way to make a quantum computer more powerful. Is this more powerful? Yes, because we have 85% chance of winning this game instead of 75. So it's a very small example of how a quantum computer can be more powerful. Again, this is useless, but it gives you an idea. If I want to show you a real quantum algorithm, I need days in order to explain something like that, because they are so complex. But the idea is the same in classical computing. We are not creating circuits for classical computers. When we create algorithms, we use libraries, we use frameworks to do all of those hard things for us. And it's the same in the quantum world. So in the quantum world, if I go back to my slides, here. We are going to open namespaces that have packages for very specific use cases. Q# and the base class library for Q# has packages for chemistry, has packages for physics that we can reuse to actually write programs. So we don't need to do this basic circuitry stuff. No, we just call functions, we call operations, and we use functionality that already exists. So that's the idea. We're going to create higher levels on top of this circuitry to actually make things work. Very cool. So that's basically it. Let's go to the end. One thing that I wanted to show you is when COVID hit, I got a question, do you want to write a book? Normally I would say no, but it was COVID. I had nothing else to do. So I said yes. And the thing that I showed you and all the explanation is basically in the book, but more extensive. So I'm basically trying to explain for a software developer, because by the way, I didn't tell you, I'm not into quantum computers. I don't have a quantum computer at home. I don't work with quantum computers. This is a hobby that got out of hand. So I'm just very interested in the topic. So I basically wrote all of my ideas on the level of a developer and not on the level of a mathematician or a physicist. So this is what's inside of the book. And by the way, it's approved by Polar Bear, so I guess it's fine. I also have one copy with me, if you want to have a look. I will put it here in front of me. And if you come to the Azure party, after party tonight, I will take this book with me. And the first one that comes up and talks to me, so I can take a picture and tell my mom I have friends, and tell me a cool thing about a polar bear that I don't know, you will get the book for free. And with that, that's the end of my presentation. Thank you. If there's questions, I'm here, and have a nice continuation of your conference.